Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight, we find ourselves gazing toward a visitor. Not a spacecraft, not a meteor, but something quieter, more ancient, something uninvited yet not unwelcome. Its name is 3i Atlas, a faint glint from the void drifting inward through the dark fabric of our solar system. Right now, it's moving through space in near silence, accompanied by companions, small, shadowy fragments, faintly visible only to the most patient eyes. A swarm, perhaps, or simply the illusion of one. These companions do not announce themselves loudly. They trail behind like memories of a shattering long ago, pieces perhaps from the same birth, or from something more recent, something we haven't yet glimpsed. Even now, astronomers debate what this collection truly is. A fragmented object? A family of travellers? The truth is not fully known, but we are watching, listening, measuring slight motions, tiny twinkles. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. And if you're joining us from somewhere around the world, we'd love to know where and what time it is as you listen. Now dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We have seen visitors before. One eye, Oumuamua drifted by like a sliver of cosmic driftwood in 2017. Then came 2i Borisov, a true comet, flaring gently as it approached our sun in 2019. These weren't just curious rocks. They were interstellar, born in other star systems, wanderers from places we'll never see up close. And now, 3i Atlas arrives. But this time, it's not alone. The story begins with a flicker. Telescopes catch a dim blur that doesn't move like other comets. Its trajectory curves in a way that no familiar solar orbit explains. It's fast. Its path is hyperbolic, unbound, just passing through. And something else, surrounding it, drifting at a respectful distance, are smaller reflections. A mist of pebbles, shards, companions. They appear to follow. It's as though 3i Atlas carries a retinue. Not a solid comet body shedding a tail as we see with standard comets, but a true swarm, a ghostly echo of a past event. Perhaps it broke apart long ago, or perhaps it was never whole to begin with, a cluster born scattered. We don't know yet. But what we can say is this: the fragments mirror its course, keeping a kind of loose formation, too faint for the naked eye, but traceable across time if we're patient enough. It's strange, watching something arrive from between the stars. We often imagine space as empty, a void. But the distances between stars, those trillions of kilometers, are not entirely barren. Occasionally objects are flung outward from the violent birth of planets. Icy remnants, rocky leftovers, drift out of their home systems and into the galactic current. Some take thousands of years to reach us, others millions. They do not aim, they merely continue. And yet here it is, 3i Atlas, named after the survey that first noticed it. And near it perhaps dozens of shadows, a debris field or something more deliberate. For now, we whisper guesses. Perhaps it passed too close to another star and cracked. Perhaps it was already falling apart before it even entered interstellar space. Or perhaps, just perhaps, it's the survivor of something stranger. A collision, a disruption, a ripple in the fabric of another solar system entirely. Our instruments have become more sensitive in recent years. Surveys like Pan-STARRS, the Vera C. Rubin Observatory, and of course Atlas itself, constantly scan the skies for anything moving against the backdrop of stars. They see motion not with their eyes, but through algorithms, comparisons, the patient subtraction of one night sky from the next. And in those changes sometimes we glimpse movement, unusual arcs, high velocities, unexpected arrivals. This is how we found the earlier interstellar visitors. Each time they passed quickly, just months between discovery and departure, and each time they left us with more questions than answers. But 3i Atlas lingers, not long in cosmic terms, but long enough to track with detail, and long enough to notice its companions. The swarm following 3i Atlas is not like a comet's tail. It doesn't spread in a luminous stream. Instead, it trails at varying distances, perhaps even on slightly separate paths. It might be gravitationally bound to the main object, or it might not. It's hard to know at this distance. That's the thing about deep space. Everything is faint, motion is subtle, shadows and specks blur together, and it takes weeks, sometimes months, to confirm even the simplest details. But this uncertainty is not frustrating. It's part of the wonder. Each data point we collect is a fragment of a greater story, and tonight, we get to imagine what kind of story that might be. Perhaps 3i Atlas was once part of a larger body, an interstellar planetesimal, fractured during formation. Or maybe it passed through the outer edge of a young system nudged by a giant planet and scattered like glass across the void. Its companions might be tiny, pebble-sized, dusty, or they might be small comets in their own right, each carrying a different memory of origin. As we continue, we'll drift outward and backward, toward where such objects might have come from, and what forces could cause a swarm to form and follow across such impossible distances. But for now, let's watch from our quiet vantage point here, somewhere near the sun, as 3i Atlas and its silent train of companions approach, carried by momentum, guided only by gravity and chance. Out there, they do not know we are watching, but we are, with gentle curiosity, with hush in our breath. From our quiet place beneath the velvet sky, we drift further into the mystery of visitors between stars, objects like 3i Atlas that arrive unannounced, untouched by any prior orbit of our sun. These are not simply wayward comets or tumbling asteroids. They are something else entirely, messengers from beyond. To understand what makes 3i Atlas so unusual, we have to pause and think about the borders of home. Our solar system is vast, but it has limits. The planets orbit in tidy ellipses, with most objects trapped in stable cycles around the sun. But a very few, like 3i Atlas, are not bound. They do not come from our own dusty nursery. Their paths are hyperbolic, indicating they are passing through once, and once only. That's what defines an interstellar object. It began for us with a shock. In 2017, the first known interstellar object ever detected entered our view. We named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first, and it was like nothing we had seen before. Long and narrow, tumbling oddly, it reflected light unevenly. It showed no obvious tail, no outgassing. Some proposed it was a fragment of a larger body. Others imagine icy hydrogen, or even something more artificial, though no evidence ever confirmed such ideas. Then came 2i Borisov in 2019, a very different traveller. This one was clearly a comet, spewing vapour and dust as it neared the sun. It had a textbook coma and a faint tail. It moved fast, over 30 kilometers per second, and its chemistry was slightly different from comets in our own solar system. Its arrival confirmed that interstellar visitors were not just a curiosity, but likely common. We had simply been too blind, too slow, or too focused on other things to notice them before. And now, 3i Atlas. Each of these messengers shares something in common. They're fast. They approach on trajectories that defy capture. Like stones skipping across a pond surface. We cannot pull them in. They will not orbit us. They come, drift near the sun, and continue outward, forever gone. But something makes 3i Atlas stand apart from even these strange cousins. It's not just the path or the speed, it's the company, the trailing fragments, a possible swarm. We know swarms exist within our own system. Jupiter's Trojan asteroids ride ahead and behind the giant planet. nestled in gravitationally stable regions. Meteoroid streams follow old comets, stretching out like faint echoes of past outbursts. In these cases, the structure is clear, shaped by orbital mechanics and solar tides. But a swarm from another star, that's something else entirely. To imagine how this might happen, we must look far back into the process of planet formation itself. Picture a young star system, a spinning disk of gas and dust rich with collisions, turbulence, and early planets shifting through the chaos. It's not a quiet nursery, it's more like a storm of boulders, swirling, smashing, growing, breaking. In such a place, it's easy to imagine a fragment, an icy shard or rocky core getting flung outward. Maybe it came too close to a giant planet. Maybe it was nudged by a nearby star. Whatever the cause, it found itself ejected, not just once, but perhaps in a cascade, an entire group of fragments flung outward together, carrying with them the fingerprints of their shared origin. And they kept going. For thousands of years, then millions. They passed beyond their home star's influence, entering the vast gulf between systems. The interstellar medium, thin, quiet, but not empty, became their ocean. They drifted, slowly separating from one another, yet perhaps staying loosely clustered, until now, until one fragment, which we call 3i Atlas, entered our neighbourhood, and with it, possibly others. Astronomers suspect this possibility because of slight trails observed near the primary object. They are not easy to detect. Some of them might only be visible as brief flashes or subtle dips in light. It's possible they are not even gravitationally bound to 3i Atlas anymore. But if they share its path, its velocity, its distant origin, then they remain siblings in all but distance. It would be the first time we've ever seen a true interstellar swarm, and though we only have hints, those hints are enough to stir imagination. It invites questions. Are these fragments from the same catastrophic event? Did something collide with a protoplanet in another system? Did a binary star's gravity tear apart a young world? Did a supernova scatter nearby rubble? Or were these simply born together, flung out in the natural violence of planetary birth? We don't know. And this not knowing is what keeps us watching. It keeps the telescopes humming. It keeps our minds gently turning in the darkness. To observe these travellers is to glimpse not just distant space, but distant time. The journey of 3 Atlas and its companions may have begun before Earth had life, before the moon fully cooled. They may have passed through multiple systems, tugged by stellar winds or perturbed by galactic tides. Their surfaces may be ancient and weathered, unscarred by atmospheres or suns. Some may have never seen light until now. It's possible these objects contain exotic chemistry, elements or isotopes uncommon in our own region of space, perhaps clues to the composition of distant stellar nurseries, perhaps hints of molecules that form in colder, darker places than we can currently visit. And so, we watch, we map their trajectories, we model their shapes, we listen to the silence between them, hoping that just maybe we can catch a trace of their story. Even now, as you breathe softly and settle deeper into rest somewhere out beyond Mars, 3i Atlas continues drifting. It moves slowly against the starfield. It says nothing. But in its quiet motion, we feel the echo of 1,000 chaotic beginnings. We are not alone in our motion. The stars send whispers, and sometimes if we're still enough, we hear them. Let's drift backward now, farther than our own solar system, deeper than the faint specks of the outer planets, beyond even the Oort cloud's dim halo. Let's drift to where these visitors may have begun, to the nurseries of stars, to the swirling turbulent disks of dust and ice that surround newborn suns. Most stars begin their lives in clusters, cradled within vast molecular clouds, cool, dark regions filled with hydrogen, helium, and scattered particles. Within these clouds, gravity takes hold, compressing pockets into dense, spinning knots. These knots collapse into stars, and around them, the leftovers flatten into dusty disks, rotating like vinyl records in space. These are the birthplaces of planets and of everything else. In these disks, materials clump and collide. Dust grains stick together. Pebbles become rocks. Rocks become planetesimals, those first sturdy seeds of worlds. But not every piece finds a place. Not every orbit is stable. Some objects, too small or too chaotic, are scattered like sparks from a fire. Some of them become comets. Others become rubble. And some are launched, flinging outward, too fast to be called back. These become the drifters, the ones that leave their home stars behind. It's easy to imagine 3i Atlas beginning here, in the outer reaches of such a disk tossed outward by a forming gas giant or pulled by the delicate tide of a nearby star. One moment it was part of a crowded nursery, brushing against other newborn bodies. The next, it was adrift. Perhaps it wasn't alone even then. In simulations of planetary formation, ejection is not a rare event. Many planetary systems are chaotic in their youth. Large planets migrate, disturbing everything around them. Debris scatters. Objects are either drawn inward and consumed or cast away, sometimes in groups, fragments born from the same collision or flung outward from the same spiral of instability. This might be how a swarm forms, a young system still in flux, a planet spiraling through its disk, its gravity disturbing icy planetesimals on the edge. One by one, these objects are nudged into new paths. Not all are lost, but some are given just enough energy to escape, no longer orbiting, but falling outward into the wider galaxy. 3i Atlas may be one of these, a fragment ejected long ago, perhaps accompanied by others that were once neighbours in its chaotic corner of space. There's something poetic in that thought, that these fragments, though no longer bound by gravity, may have retained their alignment, their drift, carried along similar trajectories like leaves on a wind, a gentle companionship across deep time. Of course, space is vast. Even a small angular separation can become light years of distance over millions of years. Most ejected fragments likely disperse quickly, but some may remain within the same corridor, like droplets in a stream. That may be what we're seeing now with the companions of 3i Atlas, a glimpse into the possibility that some swarms can survive, drifting across the galaxy not in tight formation, but in soft statistical alignment. To trace their journey is nearly impossible. Interstellar space offers no landmarks, no trails, no fingerprints, just background stars moving slowly themselves as the entire galaxy churns and drifts in its own quiet spiral. But our models help us imagine. Based on velocity and trajectory, astronomers can estimate where these visitors might have come from. Not a pinpoint origin, but a region, a direction. It's thought that 3i Atlas likely came from the direction of the Hercules constellation, a region dense with stars, with many young systems still forming. It's a guess shaped by backwards projections, by subtracting the gravitational influences of the sun and planets from its motion. But perhaps where isn't the most important question. Perhaps what matters is how. How something so small could survive a journey that spans millions, or even billions, of years. How it kept enough of its structure, enough of its motion to arrive here, within range of our telescopes. And how fortunate we are to live in a moment when we can see it. 100 years ago we wouldn't have noticed. The instruments weren't sensitive enough, the sky was too large, the signals too faint. And 100 years from now, who knows? Perhaps we'll be watching these objects from the outer edges of our system, not from Earth, but from some station near Neptune or Pluto. Perhaps we'll send out gentle probes, quiet messengers of our own, to rendezvous with such fragments, to sample their ices, to scan their structure, to learn firsthand what stories they carry locked inside. But for now, We only watch, and what we see is hauntingly beautiful. An object with no orbit, no history in our sky, no expectation of return, accompanied perhaps by pieces of itself or of its past. Some of those fragments may be too small to track. Others may never pass close enough to reflect sunlight, but their presence, faint though it may be, hints at a much larger story than a single rock from space. It speaks to the violence of formation, to the randomness of trajectories, to the quiet drift of objects that will never again see the place where they began. And as we trace their path, we're reminded that everything we see, every planet, every star, every glimmering object is still in motion. Nothing stands still, not even us. Our Earth orbits the sun moves through the galaxy, and the galaxy itself spirals slowly within a broader web of structure that spans the cosmos. We're all adrift, and perhaps, just perhaps, the swarm following Three-Eye Atlas is not unusual, but typical. Perhaps such groups drift silently across the galaxy all the time. Perhaps they pass through other systems, unseen. Perhaps some have passed through ours before we had eyes to watch. Tonight we simply have the gift of noticing. Let's settle deeper now, letting the hush of deep time surround us as we drift through the dark interstellar sea where swarms may be born and where they may wander for eternity. In this quiet vastness, we imagine not just solitary fragments like Three-Eye Atlas, but clusters of objects, moving together like distant echoes of a disrupted whole. These are not spacecraft formations or precisely choreographed convoys. They are scattered companions, a diaspora of debris drifting loosely in a shared direction. Some may have started close, then drifted apart over millions of years. Others might only appear to travel together from our point of view, spatially unrelated yet momentarily aligned. But there are reasons to think swarms like this might really exist. In our own galaxy, we've seen groupings of stars, co-moving associations, born together in stellar nurseries and still travelling as siblings through the Milky Way. Why not smaller objects? After all, in the earlier stages of planetary formation, there's no neat separation between planetesimals and asteroids, comets and fragments. These categories emerge later. In the beginning, it's just material, dust and rock and ice, whipped around by gravity and chance. Simulations suggest that, in these early systems, small bodies are often ejected not alone but in clusters. Especially in systems with more than one giant planet, gravitational instabilities can create domino effects. An object pushed outward by one gas giant might pass close to another, changing course again, or even fragmenting under tidal stress. What emerges isn't always a single rock, but a swarm. Sometimes these ejections are violent, fragments flung in every direction. But other times they're more like a quiet untying of threads, a group of loosely bound bodies that peel away together, still echoing the same vector, still whispering the same origin. That may be what we're seeing now. The swarm around 3 Atlas is faint. It's not a tightly bunched cloud, like the coma of a comet. Instead, it seems more like a trail, several small, dim objects spread along its trajectory, some ahead, some behind. Whether they're truly companions or just optical coincidences remains uncertain, but their motion suggests a common story. To help picture it, think of a school of fish scattered across a great distance. Each fish moves independently, yet the group still carries the imprint of its formation. There's no center, no leader. Just a shared drift through deeper waters. If we extend this metaphor, 3 Atlas may not even be the largest or most important of the group. It's simply the brightest, the one we've noticed. There could be larger objects ahead, already past the sun. Others might still be en route, trailing behind by days or decades. Or perhaps we're only seeing the tiniest tip of a stream that stretches across light years, its members separated by impossible distances yet once born in the same chaotic breath. The galaxy is not empty. Between the stars lie clouds of gas, rogue planets, magnetic filaments, and more. But also, perhaps, these drifting families, unbound fragments that once shared a home and now share a direction. Within our own system we have analogues. The torrid meteor stream, for instance, is thought to be the debris of a giant comet that broke apart tens of thousands of years ago. Each year, Earth moves through this stream, producing fireballs in the autumn sky. The fragments remain loosely aligned, spreading out more each year, but still holding some memory of the original comet's path. Even more compelling are asteroid families, groups of asteroids that share similar orbits, likely remnants of ancient collisions. These families slowly disperse, pulled apart by gravitational nudges and subtle forces like the Yarkovsky effect, where sunlight causes small objects to drift over time. Could an interstellar swarm be similar? Imagine a massive object breaking apart in another solar system, a dwarf planet smashed by a high-speed impact, or perhaps a giant comet torn apart by a close pass with a star. Its fragments, instead of falling inward, are flung outward, escaping the system entirely. Some leave quickly, others follow over time like beads rolling off a tilted plate. Eventually those fragments reach interstellar space, and if we're lucky, very lucky, one or more pass near us. 3i Atlas may be such a piece. Its trajectory, like that of Oumuamua and Borisov, doesn't match any solar orbit. It moves too fast to be bound. Its approach tells us it came from outside, perhaps from a system we'll never identify, perhaps from a cluster of stars that has since dispersed, or from a binary star system where chaotic orbits are common. It's possible too that its swarm is simply a trail of its own disintegration. Maybe it passed through another system long ago and was partially torn apart. Or perhaps it's been shedding mass slowly, a process invisible at interstellar distances, but leaving behind a faint stream of debris. Astronomers watch closely, comparing observations night after night. They measure subtle changes in brightness, hoping to catch a flicker that signals another fragment, another companion. These observations are painstaking. The signals are buried in noise, but each detection brings us closer to understanding the swarm, not as a theory, but as something real. And still, there's so much we don't know. We don't know how tightly such fragments might remain grouped. We don't know how many pass through unnoticed each year. We don't know if the swarm is expanding, dispersing, or still coalescing from a larger disruption. But the beauty lies in that not knowing, in the mystery that surrounds these quiet travellers. It's possible we're only beginning to see the truth, that interstellar swarms may be as common as single comets, simply harder to notice. That many solar systems eject fragments in groups, and that our sky is occasionally crossed by these caravans of the lost. For now, we watch 3i Atlas, and we wonder what else might be following, what other whispers are hidden in its trail, what other fragments might be silently sharing its path. As you breathe slowly now, with the hush of the night surrounding you, you might imagine the sky filled with invisible motion, not loud, not fast, just steady, ancient, patient. And somewhere between the stars a swarm continues its long, slow journey, not searching, not fleeing, just drifting. Let's return closer to home for a moment, not to leave the mystery behind, but to see it reflected in something more familiar. Because the idea of a swarm trailing behind 3i Atlas isn't as foreign as it might seem. In fact, our own solar system is full of swarms, quiet clusters of fragments and companions moving together through space like soft echoes of older events. Take, for instance, our asteroid families. Within the main asteroid belt between Mars and Jupiter, many objects travel in similar orbits not by chance, but because they were once part of a larger whole. When a collision occurs, when one asteroid smashes into another, it doesn't always produce chaos. Sometimes it leaves behind a family, dozens, even hundreds of pieces, each with slightly different paths, but all tracing back to the same origin. Over time, these fragments spread out. Solar radiation nudges them. Jupiter's gravity shifts their courses, but they still carry a shared rhythm, a whisper of their past. We also have cometary debris streams. When a comet nears the Sun, it warms and begins to release gas and dust. These particles scatter along its orbit, and if Earth happens to cross that path, we see a meteor shower. The Perseids, the Leonids, the Geminids, all are the visible signs of old swarms, thin rivers of particles stretching across space, released drop by drop over centuries. And then there are the Trojans. These are clusters of asteroids that share orbits with planets, particularly Jupiter and Neptune. They occupy stable regions called Lagrange points, leading or trailing the planet in its path. Though gravitationally balanced, they are not fixed in place. They drift gently, forming clouds rather than points. These groups remind us that space is not made of isolated objects, but of patterns, clusters, streams, swarms. So when we consider the possibility that 3i Atlas has companions, we're not imagining something exotic. We're recognizing a familiar structure, seen in a new context. What makes this swarm so haunting is its origin, not its shape, not even its presence, but the fact that it may have come from another star. If so, then the same processes that shape our local swarms, collisions, fragmentation, slow dispersal, are likely at play in distant systems too. The rules are universal. Gravity doesn't change from one star to another. Instability, chaos, ejection, these are the quiet engines that sculpt the cosmos. And in that sense, the swarm around 3i Atlas may be more than just a curiosity. It may be a confirmation, a signal that what we see here happens everywhere, that planetary systems all experience this slow unravelling, that every star casts off its fragments, and some of them wander. It's comforting in a way to think that our system is not unique, that our swarms and fragments are mirrored across the galaxy, that we are part of a much larger pattern, one that stretches far beyond what we can see. And still, 3i Atlas carries its own peculiar silence. Unlike a typical comet, it shows limited outgassing. Unlike an asteroid, it isn't firmly inert. Its behaviour hovers in between, and the supposed swarm, if it is a swarm, remains faint at the edge of detectability. Astronomers use powerful techniques to search for signs. Light curves are analysed for fluctuations. Pixel by pixel comparisons are made across multiple nights. If a fragment reflects enough sunlight or crosses a sensitive detector, it might be seen. But it's like searching for whispers in a storm, and yet, sometimes, we do hear them. Earlier interstellar visitors like Oumuamua and Borisov came and went alone, or so we thought. We had no reason to suspect companions, but that may have been due to our instruments, not their solitude. With 3i Atlas, we're looking more closely. We're asking better questions. One of them is, how long can a swarm survive? If fragments are loosely bound, they should disperse over time. A cluster might last thousands of years, maybe millions, before spreading too thin to detect. But in the vast stillness of interstellar space, where few forces act on an object, even fragile groupings can persist far longer than we might expect. There are no atmospheres to erode them, no planetary flybys to disrupt them, only occasional perturbations from passing stars or the very slow tide of the galaxy's gravity field. So if 3i Atlas truly is part of a swarm, it could have been travelling with its companions for eons. They may have passed near other systems, perhaps even through planetary disks, disturbing dust, stirring orbits, silent intruders, unannounced. And now they drift through ours. There is no sign of danger, no threat. These objects are small. Most would vaporize if they touched our atmosphere. Others would miss entirely, continuing outward on their endless course. But their presence carries a different kind of weight, a philosophical one. Because when we see a swarm, we are seeing the aftermath of something else, a birth a break. A beginning, maybe even a death. We're seeing not just the fragment, but the memory of motion, the continuity of drift, the quiet persistence of objects set in motion long before our species ever looked up at the sky and wondered. Tonight, as you lie still, imagine the sky not as empty, but as filled with these quiet traces. Imagine hundreds, thousands of swarms like this, flowing through space beyond our sight, each one carrying the imprint of a place, a time, a history we'll never fully know. And for a brief moment, one of them crosses near us. We watch quietly. We measure carefully. We wonder gently. And then we let it go. Let us drift even farther now toward the outermost edges of our own celestial neighbourhood, out beyond the orbits of the gas giants, past the quiet realm of the Kuiper Belt, where icy bodies like Pluto wander in slow arcs. Beyond even that, into the faint and shadowed shell that surrounds our solar system like a soft halo. This is the Oort cloud, an imagined boundary, not yet seen directly, but strongly suspected. A vast, distant reservoir of icy objects, stretching perhaps a quarter of the way to the next star. If interstellar space is the sea between islands, then the Oort cloud is the fog at our shores. We don't yet know its true shape. Some believe it forms a spherical shell, others suggest it's elongated, warped by the sun's motion through the galaxy, but most agree it contains trillions of frozen bodies, fragments from the early solar system, leftovers cast outward by Jupiter, Saturn, Uranus and Neptune during their violent migrations. And here's what's quietly astonishing. Many of those Oort cloud objects may have never returned. They orbit the sun so slowly, so distantly, that their periods span millions of years. Some are so far out they're only loosely held. A small tug, a passing star, a wisp of interstellar gas is enough to unbind them. And once they're unbound, they become just like 3-eye Atlas, interstellar. It's a gentle symmetry. Some of the fragments we see arriving from the galaxy may once have belonged to other stars' Oort clouds, and in turn, our own Oort cloud may be sending quiet messengers outward, into the void, unnoticed and unmissed. Over deep time, the boundaries blur. What we think of as our solar system is porous. Its edges are soft. Material passes in and out over millions of years, creating a kind of slow exchange between stars. This helps us understand why something like 3-eye Atlas might be accompanied by others. If it was once part of a distant system's outer cloud, then it may have left not as a lone escapee, but as part of a loose stream, a family of fragments scattered by the same gravitational event. Some simulations even suggest that up to 90% of the Oort cloud may be made of material not born in our system. Captured interstellar debris, other stars' leftovers. That means the objects trailing behind 3-eye Atlas may not be strangers at all. They may be part of a much older and more familiar process, one that has shaped our sky since the beginning. And if we look closer, the similarities deepen. Many long-period comets we observe come from the Oort cloud. Their orbits are eccentric, their paths mysterious. Some plunge toward the sun only once, then vanish again. Others return on scales so vast that they outlive civilizations, and some may not return at all. We've seen comets like C2012 S1, Ison, which approach the sun dramatically before disintegrating into vapor and dust. Others, like Comet West, broke into multiple fragments, spreading out along their path in soft, curved trails. The same could be true of 3-eye Atlas. Perhaps its swarm is not a separate group, but simply its own body, breaking apart over time, each fragment carrying a piece of its past orbiting loosely, some lagging, others drifting ahead. In this way, the Oort cloud becomes a mirror, a local analogue for the kind of phenomena we now glimpse arriving from beyond, and still we can't see it directly. The objects in the Oort cloud are too faint, too far. No telescope has yet captured a clear image of one. We infer their presence only by the arcs comets take, by the trajectories that begin far beyond the planets, tracing ellipses so wide they become nearly straight lines. It's humbling to consider how much we don't see. We orbit a star, but that star is not alone. It moves through a galaxy, which in turn orbits a dark matter halo, which in turn participates in the motion of cosmic filaments, vast threads of structure that connect clusters and voids across hundreds of millions of light years. And yet here we are, on a small planet, watching tiny specks move through the sky, trying to understand their origins by the way their light flickers. Perhaps it's the quietness that draws us in. The fact that something as simple as a dim object drifting near Mars can stir such deep questions. Where did it come from? What broke it? How long has it wandered? And above all, what else is out there? The Oort cloud reminds us that we are surrounded by the unknown, not in distant galaxies, but just beyond our grasp, just a little farther out, just a little fainter. It's possible that some of the fragments we now think of as part of the Three-Eye Atlas swarm are not actually bound to it at all. Perhaps they're members of our own Oort cloud, perturbed at the same time, caught in the same observation. Perhaps their similarity in motion is an illusion, or perhaps their paths are entwined for reasons we do not yet understand. Science proceeds carefully here. Models are run, detections are compared. But there is always a space for wonder, a space between what we see and what we think we see. That's where the imagination drifts. And as you close your eyes tonight, you might picture the Oort cloud not as a barrier, but as a meeting ground, a place where fragments from other stars arrive and where our own may depart, a silent shell of possibility suspended in the slow drift between suns, and in the darkness beyond that shell somewhere, the faint light of a fragment reflects for the first time in 1,000,000 years. Perhaps that's how we first saw Three-Eye Atlas, a flicker, a change in the sky, a new piece of a story that began long before us, and will continue long after we've stopped watching. Let's linger now on the invisible hands that shape these journeys. Not the slow passage of time, though that plays its role, nor the quiet decay of a body shedding dust, but the gravitational whispers that reach across light years, subtle, constant, and immensely patient. Gravity does not shout, it tugs, it beckons, and in the case of interstellar objects, especially those arriving in clusters or swarms, it may be gravity that first set them on their path, not from a collision or explosion, but from the serene influence of a passing star or the disruptive heft of a giant planet slowly rearranging a system. Think, for a moment, of a distant planetary system, a young star still surrounded by a disk of ice and rock. Within that disk, planets begin to form, clearing paths, pulling material inward and outward. Some of this material becomes moons, some is swept into the star. But much of it remains loose, drifting, shifting, never quite belonging anywhere. When a massive planet forms, something like Jupiter or Saturn, its influence becomes dramatic. It may toss nearby objects inward where they burn up, but more often it sends them outward. It hurls them into elongated orbits, some of which escape entirely. That escape velocity, the final push, is all it takes to begin an interstellar journey, and sometimes that push is a shared one, an entire cluster of fragments, nudged by a shifting planet or a migrating resonance, may be scattered together. Not as a perfect group, but with enough similarity that they travel in parallel, a family set adrift by the same note in gravity's silent music. Later, perhaps millions of years later, that same gravity draws them toward another system, ours. But here's where it becomes even more elegant. These journeys don't begin and end like train rides. They are recursive, looped, bound by the way gravity weaves through space and time. Take passing stars, for instance. Our solar system is not stationary. It moves through the galaxy in a slow orbit that takes over 200 million years to complete. Along that path we come close to other stars, sometimes within a light year or two. That may sound distant, but to the scattered particles of the Oort cloud it's enough. A close stellar pass can disrupt orbits, pulling some objects away, pushing others inward. Some may be ejected into interstellar space. Others, perhaps visitors like 3i Atlas, may be pulled toward us. This is not rare. Simulations suggest that over the lifetime of the Sun, dozens of such stellar encounters have occurred, each one potentially releasing new waves of material from the Oort cloud and possibly capturing debris from elsewhere. So when we consider the origin of an object like 3i Atlas, we have to think in layers. Was it ejected by a planet or by a passing star? Was it part of a binary system where gravitational tides tugged it free? Or was it caught in a larger dance, pulled outward by its home system and inward by ours? These questions don't yield simple answers. That's why astronomers build models, simulations that rewind the motion of particles, factoring in known stars and their trajectories, known planets and their masses. Even then, the answers are probabilistic, maybes, not certainties. Perhaps the most important maybe right now is whether 3i Atlas is actually being followed by a true, gravitationally linked swarm, or whether what we see are simply loosely correlated fragments, each on their own subtle arc. Still, the idea of gravitational companions is not unheard of. Take co-orbital asteroids, objects that share Earth's orbit, yet are not bound moons. They travel with us around the Sun, in complex paths known as horseshoe orbits. They're not satellites in the traditional sense, but they are companions, held by the same gravitational relationships. In Jupiter's orbit, we find the Trojan asteroids we mentioned earlier, thousands of them clustered at the L4 and L5 Lagrange points, gravitational havens where an object can linger indefinitely, trailing or leading the planet. Could something like this happen on an interstellar scale? It's unlikely that true Lagrange points exist between stars. The distances are too vast, the relative motion's too fast, but the principle still applies. Gravity shapes relationships. Even in deep space, where the pull is weak, it is never absent. This leads to a striking thought. If 3i Atlas is part of a stream, a family of fragments cast out together, then they may not have needed to remain tightly bound to stay aligned. Gravity could have set their initial directions and speeds. From there, inertia and isolation did the rest. Over millions of years they may have spread out. Some moved slightly faster, others slower. A few might have collided with other fragments or been captured by rogue planets drifting in the dark. But others, like the ones we now see, continued along, kept near each other by the memory of a shared departure. And this memory is not emotional, of course. It's mathematical. It's orbital. Everything in space remembers how it was launched. That memory lives in its trajectory, in its tilt, in its speed, in the angle at which it approaches the Sun. So when we track 3i Atlas and its companions, we're not just looking at objects. We're reading old equations, set in motion long ago, solved slowly by the unfolding of space and time. Perhaps this is why watching such objects feels so intimate. They come not to speak, not to teach, not to change our course. They simply pass. They reflect sunlight. They move as they were made to move, and for a short time we get to see them, to notice, to ask. As you breathe slowly now, and the weight of your thoughts begins to soften, imagine yourself floating above the solar system, watching the arcs of these fragments unfold. Long, gentle curves drawn in silence, guided by nothing more than the invisible hands of gravity and deep time. That's how a swarm begins, and perhaps how it ends. Now we turn to the eyes with which we see, instruments that stretch far beyond the reach of our senses, delicate, precise, and tirelessly patient. Without them we would not know 3 Atlas exists. We would not see its companions. we would not hear the whisper of a swarm brushing against the outer edge of our sky. Our oldest telescopes looked upward through glass, tethered to Earth by atmosphere and weather. Even the clearest nights softened their gaze. But today, we have eyes in space. Machines that orbit above the clouds, in stillness, looking out into the dark without blinking. It was one such system, Atlas, the Asteroid Terrestrial Impact Last Alert system, that first noticed 3i Atlas. Designed to spot small, fast-moving objects before they near Earth, Atlas surveys the sky in wide swathes. Its role is practical, even urgent, to find what might strike, but in doing so, it finds much more. Atlas is not alone. Across the Earth, and high above it, many surveys work together. Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, Canada-France-Hawaii Telescope, and soon the Vera C. Rubin Observatory in Chile. These observatories don't watch the sky as we do. They do not look for beauty, though they find it often. They look for change. They photograph the sky again and again, night after night, comparing each image to the last. And when something changes, when a point of light moves where it should not, an alarm sounds, a new object, a possible visitor, a piece of motion against the stillness. 3i Atlas was one such change. Faint, fast, unusual. Its motion didn't fit the curve of a normal solar orbit. It came in too steeply. It moved too quickly. Its path, when traced backward, did not circle the sun. It passed by. That was our first clue. Then came the second. Subtle shifts in its brightness. Hints of companions. Faint trails, not consistent with a typical comet's tail, but with small objects, perhaps fragments, moving nearby. We turned more eyes toward it. Ground-based telescopes followed its arc. Some tracked it nightly. Others waited for the perfect geometry, when its position would make its companions most visible. Each new image brought more questions than answers. That's the nature of this work. In the silence of space, answers come slowly. Light travels fast, but data travels carefully. Interpreting the data requires not just skill, but quiet patience. And the tools themselves, they are remarkable. Take the Hubble Space Telescope. Though not designed for tracking fast-moving objects, it has caught fleeting images of comets and asteroids, sometimes capturing their fragments in stunning detail. Or the James Webb Space Telescope, tuned to infrared wavelength, capable of sensing heat from the coldest objects. If pointed in the right direction, it might one day study the thermal glow of such interstellar visitors, revealing their composition with a whisper of radiation. Then there are the radio telescopes, arrays like the Very Large Array in New Mexico or LOFAR in Europe, can sometimes pick up the hiss of ionized gas as it interacts with solar wind, especially in comets. They do not see light, but they hear echoes. Patterns, frequencies. Each type of telescope sees a different sky, one in visible light, another in heat, another in radio waves. When they work together, the sky becomes richer, layered like a dream with many voices. As we study 3i Atlas and its companions, we begin to build a profile. Not just where they are, but what they're made of. Are they dusty, icy, metallic? Are they active, releasing vapor and gas? Or are they quiet, dark, inert, and cold? Sometimes answers emerge slowly through light curves, tiny graphs that track an object's brightness over time. A sudden dip might suggest rotation. A subtle increase might reveal a release of gas. A repeating pattern might tell us its shape. Elongated, spherical, tumbling. Even more delicate are the trails of suspected companions. They must be teased from the noise, confirmed with follow-up observations. What looks like a nearby fragment may turn out to be a background star, or a cosmic ray, or a trick of optics. But when fragments are confirmed, the mystery deepens. How many are there? How far apart? How large? Some may be no larger than a bus, others perhaps as small as a pebble, most will never be seen. But their presence changes the story. It means we're not observing a lone traveller, but a memory of disassembly, a puzzle whose pieces are still tumbling through space. And beyond these immediate tools, there's the archive, decades of images from earlier surveys. Sometimes, when a new object is found, astronomers comb through past data to see if it was caught before by accident. If 3i Atlas passed near us once before, unnoticed, those images might still be waiting in the digital dark. This retroactive discovery is called a precovery, and it's a powerful way to extend an object's known orbit. Each data point helps refine the trajectory. Each faint dot found in an old image helps us map the past. But no matter how many instruments we build, how finely we tune them, there are limits. The swarm following 3i Atlas may contain members too faint to detect, too small, too far behind, or too recently broken off. That's where imagination steps in. Data can only go so far. After that, we model, we simulate, we ask. What would such a swarm look like? How would it move? What paths would its fragments follow? How would they spread out over time? Even now, teams are running these simulations, feeding in what we know, speed, angle, brightness, and letting the physics unfold. It's not perfect, but it helps. It builds a picture, a quiet narrative drawn from numbers and light. And from that narrative, we begin to see not just this swarm, but others, hypothetical, unseen, moving through other systems, past other stars, followed perhaps by other watchers. Perhaps right now, another planet is watching our fragments pass by. Quiet particles from our own distant disruptions drifting past alien skies. As you listen, the sky outside your window is unchanged. But in the dark between planets, the story moves, traced in motion, written in light, and we follow it, not with our eyes, but with the patient vision of machines that never sleep. As we continue drifting with the quiet trail of 3i Atlas, a new question forms in the dark. How many others are out there? For every object we discover, every flicker that resolves into a visitor, how many pass by unseen? How many swarms slip through the solar system, undetected beneath the glow of starlight, too faint to register, too fast to follow? Astronomers are beginning to ask this very question, and the answers, though uncertain, are quietly astonishing. When once Oumuamua appeared in 2017, it wasn't just its odd shape and tumbling motion that surprised scientists. It was the fact that we'd never seen such a thing before. In all the years of sky surveys, no interstellar object had ever been confirmed, and yet here one was, sudden, silent, and already leaving. Then Borisov followed just 2 years later, and now 3i Atlas, 3 interstellar visitors discovered in just 6 years. That's not a coincidence, it's a clue. It suggests that these objects are not rare. They were always there, moving silently through space, and we were simply blind to them. Our instruments were too limited, our surveys too narrow. But now, as our tools improve, the sky is opening up. And what we're beginning to glimpse is a quiet population of wanderers, perhaps even a torrent of them, passing through constantly, unnoticed. Estimates vary. Some models suggest that thousands of interstellar objects the size of Oumuamua pass through the inner solar system every year. Thousands! Most are small, most are dark. Most never come close enough or reflect enough light to be detected. But they are there. They are always there. And if even a small fraction of those visitors are swarms, fragments from broken bodies or disrupted clusters, then the idea of 3i Atlas trailing a loose group becomes not an anomaly, but a pattern. The challenge is detecting them. We are limited by light, by scale, by timing. A fragment the size of a car travelling at interstellar speed and reflecting barely any light is almost impossible to find unless it comes unusually close. And even then, we must be looking in the right place. at the right moment. But there are ways around this. Surveys like the Vera C. Rubin Observatory will soon scan the entire visible sky every few nights, generating a complete and living map of motion. With its 8.4-meter mirror and vast digital camera, Rubin will see fainter objects than ever before. It will not just catch visitors, it will catch patterns, motion across frames, the early signs of swarms. Other instruments look for movement against the static star field, automated comparisons between nights, flagging anything that shifts or flares. And sometimes we get lucky. Oumuamua was noticed because of its rapid motion. 2I Borisov was brighter than expected. 3A Atlas drew attention by moving in a hyperbolic path. These are just the easy ones, the bold ones. The others remain hidden. That's why researchers turn to statistics. If we've seen 3 interstellar objects in 6 years, what does that imply about the unseen? They build models of the galaxy. They estimate the number of planetary systems capable of ejecting debris. They factor in gravitational assists, collisions, and migrations. And from that, they estimate how many fragments are likely drifting through the Milky Way. The answer is more than we ever expected. Some estimates suggest that for every star in the galaxy, there may be tens of thousands of ejected fragments. Planetesimals, shards, frozen cores, lost moons. Some may be as large as planets, others no bigger than marbles, but all unbound, all wandering. That's hundreds of trillions of interstellar objects. And here's the quiet wonder: our solar system doesn't block them, it filters them. Most pass through unimpeded, curving gently around the sun and continuing outward. Some may linger a little longer, some may be drawn in, temporarily captured in looping orbits before they escape again. Rarely, very rarely, one might be slowed just enough to stay, and it's this possibility that opens a new frontier. What if some objects in our solar system were once interstellar, captured long ago, so long that we no longer recognize their foreign origin? We've already begun to suspect a few, some asteroids with unusual orbits. Some icy bodies in the outer solar system. Their paths don't match our typical models. Their compositions are strange. Their stories feel different. Perhaps they were born elsewhere, and now they drift among us, unnoticed, adopted by our sun, added quietly to the population. There's an open question in astronomy now. What fraction of our solar system's small bodies were born beyond it? And it's not a trivial question. It touches on the fundamental structure of planetary systems, on how common disruption is, on whether ejection is a fluke or a frequent event. It also touches on origins. If material from other stars can reach us, perhaps in swarms like the companions of 3I Atlas, then perhaps seeds of other worlds, other chemistries, other histories are always drifting among us. Perhaps the early Earth was dusted by such fragments, tiny visitors from unknown systems carrying rare elements or complex molecules, or simply new possibilities. It's not just romantic, it's testable. In time, we may gather enough data from these interstellar visitors to compare their isotopic signatures, their organic content, their mineral makeup, each piece a puzzle fragment from another system. And if we gather enough, we may begin to map not just where these objects come from, but how common such wanderers are. Perhaps we are surrounded. Perhaps the solar system is never truly alone, not just in terms of stars or gravity, but in terms of travellers, carried across vast distances, sent out by the quiet violence of formation, passing near our sun for a few fleeting months, and then fading again. Tonight we rest beneath a sky not just of stars, but of motion, of hidden visitors, of gentle swarms whose numbers we may never truly know. We count what we can, we estimate the rest, and in between we wonder. Let's return again to the idea of companionship in motion, not just fragments in flight, but entire groups of objects travelling in synchrony across space. In our own solar system, there are places where this phenomenon isn't rare. It's stable, natural, and expected. They're called Trojans. Imagine a planet like Jupiter, immense and ancient, following its slow path around the Sun. Ahead of it and behind it, in perfectly balanced gravitational zones, clusters of asteroids move with it, locked into harmony. They don't orbit the planet directly. Instead, they co-orbit the Sun, always leading or trailing by exactly 60 degrees. These are the Trojan asteroids. Thousands have been discovered near Jupiter, occupying two great swarms, one at the L4 Lagrange point ahead of the planet, and one at L5 behind. They move as a kind of celestial escort, always keeping their distance, never overtaking, never falling behind. The balance that holds them there is delicate yet powerful. The gravitational pull of the Sun and Jupiter cancel out just enough to allow these objects to remain, seemingly forever, in their shared path. And here's the connection. This kind of loose companionship, motion guided by gravity, not strict orbit, mirrors what we might be seeing with 3i Atlas and its supposed swarm. Not identical, of course. The Trojan swarms are stable and well understood, while the interstellar swarm is fleeting and poorly resolved. But both are examples of natural clustering, of motion with memory, of gravity sketching trails in the dark. Neptune too has Trojans. So does Earth, though ours are much smaller and fewer. Even Mars and Uranus have a few. In every case, these companions were likely captured early in the solar system's history, drawn into position and then held there by resonance. Could something similar happen between stars? It's unlikely that true Lagrange points exist on interstellar scales. There's simply too much motion, too many perturbations. But the principle holds that multiple objects can share similar paths, that swarms can remain loosely aligned, not because they're bound by gravity, but because they were born together and never strayed far from one another. The Trojan analogy helps us imagine the invisible structure that motion can take. We often think of space as chaotic, asteroids flying randomly, comets on reckless dives. But much of the solar system is ordered. It has rhythms, relationships, echoes, the orbital resonances of Jupiter's moons, the shepherding paths of Saturn's rings, the co-orbital dance of Trojan asteroids. These are not exceptions. They are signatures of how gravity sculpts the void into song, and so, when we see hints that 3i Atlas might be accompanied by other fragments, we're not seeing noise, we're seeing structure, motion that carries a whisper of the past. Perhaps it was once a Trojan of its own, around another star, or part of a co-orbiting cluster, broken apart by instability. Or perhaps it was part of a binary object, two fragments orbiting one another until distance tore them apart. There are precedents for that too. Some asteroids in our own system are binaries, two bodies of similar size orbiting a common centre of mass. These pairs are often the result of slow collisions, tidal forces, or spin-related breakups. Some comets split in similar ways, their parts remaining nearby for years or even centuries. Comet Shoemaker-Levy 9, for instance, was torn apart by Jupiter's gravity in 1992. Its fragments lined up in a dramatic chain, and 2 years later, one by one, they struck Jupiter's atmosphere in a series of luminous impacts. That event showed us what can happen when a loosely bound cluster meets a massive gravity well. It also showed us that fragments can remain together for surprisingly long periods, even after catastrophic separation. Could the 3i Atlas swarm be something similar? Fragments from a past breakup, still aligned after thousands or millions of years? It's possible, especially in the vastness of interstellar space, where gravitational nudges are rare and nothing comes close enough to scatter them. And what of their future? Once they pass through the solar system, these objects will continue on. The sun's gravity will alter their path slightly, curving their trajectories outward, but they will not remain. They're too fast, too free. Some may become part of the broader interstellar population, just another fragment moving through the galaxy. Others may eventually pass near another star, and their path may shift again. A few might be captured briefly, only to escape once more. In rare cases, an object might slow enough to stay. Jupiter, with its enormous mass, has the power to alter an incoming object's velocity significantly. If timed just right, a passing fragment could be drawn into a long looping orbit around the Sun. It might become a distant comet, returning once every 100,000 years, or it might settle into the Oort cloud, never to be seen again. Even Earth's gravity, though weaker, plays a role. There is growing interest in finding and studying small near-Earth objects that may be temporarily captured. These are not permanent moons, but brief companions, fragments that linger for months or years before drifting away again. They come and go like dreams. We call them mini-moons. Perhaps one day we will identify a mini-moon that is truly interstellar, a tiny wanderer from another system, captured just long enough to be studied, scanned, even visited. That is the hope behind missions like the proposed Comet Interceptor, or even more ambitious interstellar probes. To meet these objects not from afar but up close, to catch one in the act of passing, to take a sample, to send back a whisper of its composition, its age, its story. Until then, we can only imagine. Imagine a sky filled not just with planets and stars, but with travellers. Imagine them moving in loose lines, trailing behind faint leaders. Imagine some moving in pairs or trios. Imagine fragments carrying memories of impacts, of migrations, of disruptions we'll never see. Imagine, even now, a fragment trailing just behind 3i Atlas, too small to detect, too dark to reflect, but keeping pace, keeping company, just long enough to pass near the Sun, and then fading again. We drift now into the quiet heart of what these visitors might carry. Not just ice or rock, not just trajectories or velocities, but chemistry. The elemental signatures of where they came from. The dust and molecules etched into them by time, by formation, by the quiet breath of interstellar space. Because every object, even the smallest grain, is made of stories. And when it comes to objects like 3i Atlas, objects that may have journeyed for millions of years across starless voids, those stories are precious. Their surfaces are ancient, their interiors untouched. They carry in frozen stillness the memory of other suns. What might such a fragment contain? We know from studying comets and asteroids in our own system that small bodies are surprisingly rich in complexity. They carry water, carbon compounds, silicates, metals. Some contain complex organic molecules, long chains of carbon and hydrogen, sometimes with oxygen or nitrogen mixed in. These molecules are not life, but they are the scaffolding, the alphabet. On Earth, we think of organic chemistry as something that happens in oceans or cells or labs, but in space it begins in dust, in cold, quiet clouds, in the shadowed corners of disks around newborn stars, where ultraviolet light and cosmic rays stir reactions in the thinnest films of ice. Methanol, formaldehyde, acetylene, hydrogen cyanide, even simple sugars. We found them on comets, we found them in interstellar gas, and we suspect that the building blocks of life are not rare, they are common, written into the fabric of space like the soft background hum of a lullaby. So when we imagine 3i Atlas, trailing a possible swarm of siblings, we imagine not just stone and silence, but chemistry, perhaps exotic, perhaps familiar, but ancient either way. To study it, we would need a sample. In our own solar system, we've begun to do this. Missions like Japan's Hayabusa 2 returned grains from asteroid Ryugu. NASA's OSIRIS-REx is bringing material from asteroid Bennu. These particles, tiny, barely visible, are analysed with the finest instruments on Earth, and what they reveal is astonishing. Hydrated minerals, primitive carbon compounds, materials unaltered since before the planets formed. Now imagine doing the same with an interstellar fragment. It's possible, perhaps even likely, that 3I Atlas or one of its companions contains materials we've never seen, isotopes in unfamiliar ratios, dust grains formed around stars unlike our Sun, ices that condensed in colder, more distant regions, even pre-solar grains, particles that predate the birth of our own star. Each one would be a message from somewhere we cannot visit, a physical poem from another world. But even without direct samples, we can study from afar. Spectroscopy, our ability to split light into its component wavelengths, allows us to read the fingerprints of elements and molecules. When light reflects off an object, or when a comet's coma glows with sunlight, its spectrum tells us what it's made of. We've used this method to study 2I Borisov, which showed signs of cyanide gas and carbon chains, similar to what we see in local comets, but with slightly different balances. That difference was small, but it told us something powerful. Chemistry in other systems might not be wildly different. The rules may be universal, but that's just one data point. We need more. 3I Atlas offers another opportunity. If its swarm contains active fragments, ones that release gas or vapour as they near the Sun, we may catch their spectra. Even faint emissions captured with careful instruments can reveal secrets. We might see common ices, water, carbon dioxide, ammonia, or we might see rarer compounds, things that formed in more extreme environments, things that challenge our models. And what if one day we find something unexpected, a molecule we didn't predict, an isotope ratio that doesn't make sense, a mineral that shouldn't form in known conditions? These discoveries would not just add to our knowledge, they would reshape it. They would suggest that planetary formation, the process that made Earth, is just one version among many. That life too might be just one version. We are far from that revelation. But the path begins here, with fragments like 3I Atlas, with the dust they carry, with the chemistry they shield from the heat of stars and the erosion of atmospheres. These fragments are vaults, ancient, sealed, uncorrupted. They do not burn with energy, they do not shout, they drift, slowly, silently, but they carry everything. It's worth noting that even our best instruments struggle to capture these details. We need extremely sensitive detectors, careful timing, and clear skies. And sometimes we see only the outermost layer, a hint of vapour, a glint of sunlight, a shadow across a sensor. But even these whispers add to the story, and the story is this. We are not the first place where chemistry became curious. Long before Earth cooled, long before the moon formed, long before the sun itself ignited, particles were dancing in the dark, colliding, sticking, reacting, forming patterns that would later seed stars, disks, planets, and maybe more. Some of those particles remain, frozen, preserved. Perhaps one of them is passing near Mars now, trailing behind a dim fragment called 3I Atlas. Perhaps it carries within it the same ingredients that once fell upon the early Earth. Or perhaps it carries something new. We may never know. But the possibility changes us. Because once you've imagined a dust grain crossing the galaxy for 1 billion years, carrying a fragment of another star's story, the night never looks quite the same. And as you rest tonight, letting your breath soften, perhaps you'll feel it. That trace of curiosity, like a particle in your palm. Something small but ancient, something cool but filled with quiet fire. And perhaps, in that hush, you'll wonder what other chemistries are out there, what other swarms, what other stories. Let's drift now into a quieter question, one that hums beneath all the others. What happens if one of these fragments touches us? It's an unlikely event, to be sure. Space is vast, and even when objects pass through our solar system, most remain far from Earth, tens of millions of kilometers away, slipping by with barely a gravitational nod. Still, the question lingers like a breeze in the background. Could a fragment from the 3I Atlas swarm, or one like it, ever reach us directly? If so, what would it mean? Let's begin with the science. The majority of objects in space, especially those the size of a pebble or a fist, are harmless. If they enter Earth's atmosphere, they burn up as meteors, brief glowing streaks in the night sky. Even larger pieces, the size of basketballs or even washing machines, tend to disintegrate before reaching the ground. But what if one fragment of 3i Atlas, or another traveller like it, were large enough and dense enough to survive the journey through our atmosphere? It would become a meteorite, a piece of deep time, fallen to Earth. And that would be extraordinary, because it would mean that a rock, formed in a system not our own, had travelled across the interstellar medium, drifted through the chaos of our solar system, and come to rest on a quiet patch of ground, perhaps in a desert, or an ice sheet, or the floor of a deep ocean trench. A rock older than the sun, nestled in the palm of a scientist. We might already have such meteorites. Some researchers have proposed that certain fragments recovered on Earth, specifically a meteor known as IM-1, which entered the atmosphere in 2014, may have interstellar origins. Its trajectory, when traced backward, suggests it was not bound to the Sun. Its composition may be unusually tough, hinting at dense materials formed under different stellar conditions, but confirmation is difficult. Without clear markers, chemical fingerprints that definitively differ from all known solar system sources, we cannot yet say for certain. Still, the possibility has changed the conversation. For the first time, scientists are organising expeditions not just to retrieve meteorites, but to search specifically for those that might not be from here. It's a quiet revolution. And it could grow louder if 3 Atlas were to contribute one of its own. Yet even if no fragment ever reaches Earth, there's another possibility: interaction. If an object passes near a planet, say Mars or Jupiter, it might be caught briefly in its gravity well. Not captured forever, but deflected, slowed, maybe even fragmented by tidal forces, this too leaves a mark. Imagine, for example, a fragment from the 3i Atlas swarm brushing against Mars' thin atmosphere. Not enough to crash, but enough to scatter dust, to ionize a trail, to leave behind a transient whisper that orbiters could detect. Instruments like MAVEN or the Mars Express could, in theory, sense such disturbances. These would be small events, barely perceptible, but they'd be real. A physical interaction between our solar system and another's relics. Or consider the Moon. Its surface is exposed. No atmosphere, no weather, no protection. Every tiny impact, even from a grain of sand, leaves a mark. A visitor from beyond the stars could strike the Moon and carve a miniature crater. And in that crater, for millions of years, the story of a passing swarm might be etched in silence. We might only find it centuries from now, or never. But even without direct impact, even without dramatic collisions, the presence of interstellar fragments changes our sky. It redefines what we mean when we say here and there. The moment a fragment from 3i Atlas crosses into the solar system, it becomes part of our domain. Briefly, temporarily, not captured, but acknowledged. Its path bent slightly by the sun, its future reshaped, and perhaps the most poetic interaction of all is this: light. As these objects pass, they reflect sunlight. Not much, not brightly, but just enough for us to see them. Tiny signals against a field of stars. That reflected light is not merely illumination, it's communication. The angle of reflection tells us the shape of the object. The colour tells us its composition. The dimming and brightening over time reveals rotation, texture, perhaps fragmentation. Light becomes our conversation with the swarm. It is a language without words, without sound. And yet, it tells us that the object is there, that it's real, that it's moving, that it's older than anything we've ever touched. This is why astronomers look so carefully, why they wait, night after night, tracking slight changes, why they calculate orbits again and again, refining trajectories until they can say with confidence, this object is not from here. because every time that happens, our understanding expands. We begin to see our solar system not as an island, but as a harbour, a place that travellers pass through, a region crossed by currents we cannot fully chart, and with each pass, each trail, each faint companion glinting behind a brighter fragment like Three-Eye Atlas, we ask the same thing. Will one reach us? Has one already? Will we know when it happens again? These questions aren't urgent, they're not alarming, they're gentle, like waves lapping at a distant shore, and perhaps that's the best way to receive them, not with fear or expectation, but with quiet wonder. Tonight, as you close your eyes, imagine one of these fragments slipping silently through the upper atmosphere, too small to see, too fast to stop, leaving behind nothing but a momentary shimmer, a streak of heat, a breath of gas, a trail of particles falling gently to Earth. You wouldn't hear it, you wouldn't feel it. But far above, gravity and chemistry would have danced, and for a few seconds, the sky would remember. Let's lift our gaze beyond the immediate to timescales so vast they blur the boundary between past and future. The journey of Three-Eye Atlas and its companions, if indeed they are a swarm, did not begin with our noticing, and it will not end when they fade from view. Their story, like so many in the cosmos, unfolds across epochs. To imagine their full journey is to think in millions, millions of years, millions of kilometres, millions of silent revolutions. What we see now is only a crossing, a moment. Perhaps these objects began as parts of a distant world, icy crusts or dusty satellites orbiting a forming planet. Perhaps they were stirred by a sudden change, the migration of a gas giant or the quiet pull of a companion star. That moment, brief by geological standards, set them loose, and once they were unbound, their path grew long. They passed through the chaotic edges of their home system, then beyond it entirely. Past Oort-like clouds, if their star had them, past bow-shocks and magnetic boundaries, into the raw, thin sea of interstellar space. There they drifted, unheated, untouched. For how long? We can only guess. But some estimates place Three-Eye Atlas's journey in the range of tens of millions of years, perhaps longer, and all that time, it was silent. No motion relative to its own frame, no weather, no erosion, just the slow passage of stars overhead. It may have passed near others. In the galactic disk, stars pass one another routinely. Every few 100,000 years, our own sun drifts near another system. Their gravitational fields brush. Sometimes this perturbs distant objects, sending comets inward or scattering small bodies outward. And so, as we imagine the swarm of Three-Eye Atlas moving through space, we must imagine it as something constantly on the edge of change. Even the gentlest gravitational touch, a faint tug from a passing star, could have altered its course. Over millions of years, such nudges add up. A curve here, a pull there, a slight deceleration, a deflection. Not enough to bind the object to another star, but enough to shift its trajectory across the sky by just a few degrees. Eventually, that path brought it near our sun. We often speak of the cosmos as vast, and it is. But paths do cross, objects do align, and in this case something unbound came close enough for our instruments to notice, just in time. If we had been watching a few years later or earlier, we might have missed it. That's how fine the window is. But what this tells us is something deeper. These crossings are part of a constant story. Not rare miracles, but inevitable events. The galaxy is full of drifting debris, some created during formation, some left behind by collisions, some, perhaps most, never noticed. And that raises another haunting question. How many such crossings have already occurred? Before we had telescopes, how many interstellar objects passed through the solar system undetected? Before humans, before Earth had eyes at all, how many fragments from other stars swept silently past? It's almost certain the answer is many. In fact, Some researchers believe that Earth itself may have been seeded by such material, that long ago fragments like these, swarming in from distant stars, delivered rare isotopes, water or organic compounds, not in a single moment, but over time, a quiet, cumulative rain of the unfamiliar. Perhaps the early Earth received thousands of such impacts, microscopic grains buried in silt, tiny pebbles lost in lava flows, dust scattered into the atmosphere. Nothing large, nothing apocalyptic, just a steady exchange of materials across cosmic time. This idea is part of a larger hypothesis known as panspermia, the notion that life, or the building blocks of life, may spread between worlds, not by intention, but by accident, by drift. It remains speculative. We have no proof, but the possibility continues to haunt the edges of astrobiology, and if it is true, then a fragment like 3I Atlas may not just be a traveller, it may be a carrier, not of life necessarily, but of potential. Even if it never touches a planet, even if it simply brushes past the sun, arcs gently outward and returns to the dark, it may still be part of a cycle larger than any one star system, a cycle of movement, of chemistry, of quiet diffusion. It's important to remember, too, that these processes work both ways. As objects like 3I Atlas enter our system, others may be leaving. Ejected by Jupiter or by close encounters with Saturn or Neptune, some comets or asteroids may gain just enough energy to escape the sun entirely. Once unbound, they drift outward, forever. Some will cross into the domain of other stars, some may enter their Oort clouds, some may fall inward, unnoticed, like faint messages from our corner of the cosmos. And so we begin to see the galaxy not as a static map of stars and planets, but as a dynamic, drifting ocean of material. Slow, interwoven, ancient, the sun too moves. It orbits the galactic centre once every 230 million years. In that time, its position relative to other stars changes constantly, and with it, the flow of objects, arriving and departing, shifts like tides. We may be in a calm region now, or perhaps a busy one, we can't yet say. But with each detection, Oumuamua, Borisov, 3I Atlas, we begin to trace the flow, we begin to sense the current, and as we track these objects, we realise that the sky we see is not fixed, it is full of motion, full of crossings. You might imagine it now, a night sky not just of stars but of faint, undetected trails, lines etched across centuries, some converging, some parallel, some fleeting, each one the signature of a journey that began before us and will continue long after. The Atlas is one such line, and if it is indeed followed by a swarm, if those companions are real, then we are witnessing not just a visitor, but a caravan, a memory of something broken, or scattered, or born together, now passing silently through our light, just for a moment. We turn now to the strange way gravity bends light, not just as a force that tugs at matter, but as something that can reshape vision itself. It's a phenomenon known as gravitational lensing, and though it may seem far from the drifting path of 3I Atlas, it too speaks to the hidden structures of the universe, because what we see is never quite the whole. Gravitational lensing happens when a massive object, like a star, a planet, or even a clump of dark matter, sits between us and something farther away. The gravity of that middle object warps the fabric of space-time, bending the path of light like a lens. Sometimes this results in arcs. Rings, mirrored images. Other times it causes a distant object to flicker briefly brighter, magnified not by its own power, but by a coincidence of alignment. But why mention it here, as we drift alongside 3I Atlas and its potential swarm? Because gravitational lensing teaches us a quiet truth. Objects don't always reveal themselves directly. Some are known only through the ways they affect what we see around them. This may be the case with parts of the swarm. If 3i Atlas is accompanied by smaller fragments, some may be too faint to reflect light toward our telescopes, but they may still affect light from the stars behind them, a dimming, a brief distortion, a flicker in the background sky. These subtle effects, called occultations and microlensing, are being used more and more to detect things we can't otherwise see. From exoplanets to rogue worlds, from comets to distant moons, this method allows us to sense the unseen. Imagine a fragment the size of a house, trailing behind 3i Atlas. It has no outgassing, no reflective tail. It's dark, cold, quiet. But as it passes in front of a background star, it blocks the light for just a moment. A blip, a shadow. Sensitive instruments catch it. Astronomers analyze the timing, the shape, the duration, and from that, they infer size. Speed, distance. It's not imagination, it's measurement. In shadows. This is how we're learning to see swarms, not just as clusters of dots, but as networks of influence, as fields of movement, as whisperers of light. The gravitational environment of our solar system too plays a role. As 3 Atlas passes near planets, its trajectory is slightly altered, not captured, but curved, tilted, redirected, and with it, any fragments nearby. These tiny changes are hard to measure, but they accumulate. A small gravitational nudge near Jupiter may shift an object's path enough to affect where it will be in 1,000 years, or 10,000. And so the shape of a swarm can be stretched by these interactions. Its members, once close, may drift apart. Others, farther away, may be pulled briefly closer. In a sense, the swarm is sculpted as it passes, by gravity, by light, by the slow dance of orbits and alignments. There's another layer to this. If 3 Atlas passes near other debris, undetected dust fields, ancient comet trails or particles left behind by long-dead comets, it may temporarily alter their paths too. A cloud of fragments moving through space is not like a solid object. It's more like a breeze, and sometimes that breeze leaves fingerprints, not just in motion, but in illumination. A sudden glow, a new reflection, a faint light curve that wasn't there before. These are the signs that astronomers chase, and sometimes, just sometimes, we get a double reward, lensing and reflection. A gravitational shift combined with a flash of light, like catching both the shape and the shimmer of something nearly invisible. This is especially true near the edge of detectability, where our instruments push their limits. We may not see the fragment directly, but we see its signature, its passage, its trace, like footsteps in frost. In the future, as more sensitive space telescopes come online, we may begin to catch such signatures more regularly. Missions like Nancy Grace Roman's Space Telescope, designed to map dark energy and exoplanets through microlensing, may also stumble across faint swarms of interstellar origin. And when they do, we'll begin to trace patterns. Because one fragment is a curiosity, a second is coincidence, but a third, a fourth, a cluster, that begins to form a thread. And from those threads, we can build maps, not just of objects, but of paths, of highways through the galaxy, of places where fragments move, again and again, shaped by the soft pressure of mass and time. Some researchers even speculate that there may be preferred routes, corridors through the galactic disk where debris tends to drift, nudged by the cumulative pull of the stars, the arms of the galaxy, and the bulk of invisible matter. In this view, 3i Atlas isn't just an object, it's a traveller on a current, a participant in a system wider than the solar system, wider even than the sun's influence, and its companions, if they exist, are not just scattered fragments, they are markers, points on a curve we're only just beginning to trace. It's humbling to think that gravity, which we feel daily as simple weight, is also the sculptor of galaxies, the deflector of starlight, the slow arranger of interstellar swarms, and that by watching it work, not directly, but through how it alters what we see, we can glimpse things we could never otherwise know. As you breathe more deeply now, letting the quiet settle around you, imagine the sky filled not just with light, but with lensing, with subtle warps, with invisible patterns made visible by motion. Imagine a fragment drifting past a distant star, causing a flicker so small that only one telescope in the world sees it. But that flicker tells us there is something there, something moving. Something ancient, something real. Let's now venture into the unseen. We've spoken of ice, dust, gravity and light. We've traced the paths of known fragments and considered the chemistry of their trails. But there is something else moving through space alongside them, something larger, quieter, and almost entirely invisible. Dark matter. It doesn't glow, it doesn't reflect, it doesn't interact with light in any measurable way, and yet, by all accounts, it outweighs everything we can see. Galaxies rotate faster than they should. Clusters of stars cling together when gravity from visible matter alone shouldn't be enough. Light from distant quasars bends more than expected. These effects, small but undeniable, all point to the same silent presence. Mass we cannot see. And within this hidden mass, scientists believe there may be structure, clumps, halos, and perhaps even swarms of dark matter particles moving through space in patterns of their own. Could swarms like the one that follows 3 Atlas somehow echo or reflect this deeper, darker architecture? The idea is compelling, because if regular matter, rock, ice, dust, can be flung outward in arcs and trails, surely dark matter too must obey the same gravitational principles. It's not bound to atoms, but it still responds to gravity. It moves, it clusters. It forms halos around galaxies and threads between them. Simulations of cosmic structure, vast maps of the early universe, show this clearly. When scientists model the growth of galaxies from the Big Bang onward, dark matter is always the scaffolding. It collapses first, it forms filaments and knots, and into those knots regular matter falls. Gas, dust, stars, planets. So it's possible, perhaps even likely, that as interstellar objects like 3I Atlas travel through the galaxy, they pass through invisible clouds of dark matter. We wouldn't see it happen, but it would be there. And what if, in some distant system, a region of dark matter was just dense enough to shape the early evolution of a planetary system, to tug gently on its outer disk, to create perturbations that scattered objects outward in soft statistical alignment? What if the formation of a swarm like 3I Atlases wasn't just a gravitational coincidence, but a result of deeper, unseen scaffolding? These are open questions, and they remain speculative. But the parallels are striking. A swarm of fragments, too faint to see individually, moving together in a loose formation. This description applies both to what we think dark matter does, and to what we now see with objects like 3I Atlas. Both are quiet, both are ancient, both are shaped not by collisions but by motion, and the resemblance goes further still. The paths of dark matter through the galaxy are believed to be complex, not linear, but curved, sweeping gently through space, pulled by galactic arms, twisted by massive clusters, drawn into filaments. These paths may overlap with the ones we're now detecting for interstellar debris, perhaps not precisely, but closely enough to hint at a hidden geometry, one that stretches beyond what we can observe directly. There's even a possibility that small, dense clumps of dark matter, so-called subhalos, pass through our solar system from time to time. They would be undetectable by ordinary means. They'd cause no flash, no tail, but their gravity might nudge comets from the Oort cloud, trigger subtle shifts, even produce patterns we don't yet recognize. Could such a clump, passing through another system, be responsible for scattering a cluster of fragments outward? Could a swarm like 3i atlases be shaped not only by the dynamics of visible planets, but by something far more elusive? We cannot say, but the thought itself opens a wider window. It reminds us that what we see in the sky, the occasional flicker, the passing object, the reflected light, is only a fraction of what's moving. The true structure of the cosmos is layered, interwoven. Light traces only the surface. Beneath it lies gravity. Beneath that, dark matter. Beneath that, perhaps deeper principles still, unknown forces that shape time, motion, and matter itself. And so, when we look at 3i Atlas, and perhaps its trailing swarm, we might also be looking at a kind of echo, a visible ripple riding atop an invisible sea. It's worth noting that our solar system, too, may be moving through regions of slightly higher dark matter density. We orbit the galactic centre, passing through arms near clusters, across filaments. Some years, we may be swimming in thinner waters. Other times, we may drift through clouds of the unseen. Could these passages affect the number of interstellar objects we detect? Could they alter the rate at which fragments enter the inner solar system? Again, we don't know. But even asking the question pulls us into deeper thought. It connects the motion of a tiny fragment, perhaps no larger than a mountain or a car, to the scaffolding of galaxies. It suggests that the swirl of dust around a distant star and the structure of dark matter on megaparsec scales might not be entirely separate, that everything, large and small, moves within the same frame, obeys the same pull. Perhaps this is what makes the idea of a swarm so quietly powerful, not just because it suggests a history of fragmentation or a shared origin, but because it mirrors a larger truth, that things move together, not always tightly, not always visibly, but together nonetheless, and that even in the silence of deep space, even in the absence of light, the universe is threaded with companionship. Not in the way we think of it, but in alignment, in drift, in paths that cross and echo and continue. Tonight, as your thoughts soften and the hush settles over your room, imagine a world where every speck of matter rides within an unseen web, where every fragment is part of a filament, where even the loneliest object carries with it the shape of something larger, and somewhere in that web a small faint visitor like 3i Atlas continues its journey, accompanied not just by fragments we can see but by shadows we cannot. Now we follow the path into uncertainty, not the soft mystery of the unknown, but the mathematical beauty of chaos itself. Because as precise as the cosmos may seem, as orderly as the planets move and the stars burn, the orbits of small bodies, like 3i Atlas and its possible swarm, are never truly simple. They are shaped by a principle both elegant and humbling, chaotic dynamics. It begins with the fact that small differences grow. A pebble nudged ever so slightly in one direction may, after enough time, end up millions of kilometers from where it would otherwise have drifted. A fragment passing near a planet may be tugged not once, but many times, each interaction layering complexity onto its path. This sensitivity is at the heart of orbital chaos, and it means that even if 3i Atlas and its companions began in near-identical trajectories, over millions of years they may have diverged, some slightly, some dramatically, scattering in ways we may never fully reconstruct, and yet the signature of their shared beginning may still be visible, a faint echo in alignment, a pattern in their spacing, a clustering of velocities, as though they remember just barely that once they were one. In the language of dynamical systems, these are initial condition-dependent processes. The further you try to predict into the future, or rewind into the past, the less confident the model becomes. This is not because the physics are wrong. The laws of gravity are beautifully stable. It's because the system itself is nonlinear. Small inputs don't produce small changes. They produce possibilities, branching paths, bifurcations and cascades. In the case of 3i Atlas, This means that what we observe now, a trail of possible fragments scattered across space, may have once been a much tighter swarm, or it may still be forming even now as the main body sheds pieces too small to yet detect. Either way, the cloud we see, or suspect, is not static. It is in motion, in flux, caught in a dance of drift and divergence, and over time the swarm will spread. This is not a guess, it is a certainty. All loosely associated objects, unless tightly bound by gravity, tend to disperse, some faster than others, but always outward, always away. And so if we are indeed witnessing a true interstellar swarm, we are seeing it at a moment of coherence, a brief alignment, like birds in flight, that will not last forever. This is part of what makes the observation so valuable and so fleeting. Astronomers know this. That's why they rush to collect data before the object grows too dim, before it passes behind the sun, before the fragments vanish into the blur of background stars. Because once the swarm disperses, its story becomes harder to tell, and yet some parts of it remain legible. We can measure rotation, we can estimate surface composition, we can model orbital evolution, and from this we learn not just about one object, but about the nature of chaos in space. There is a quiet beauty to this. We often think of chaos as disorder, but in physics, chaos simply means sensitive dependence on initial conditions. A system can be deterministic and still unpredictable, governed by clear rules and yet forever slipping beyond forecast. This is the nature of the interstellar swarm. Even if we could trace every fragment back to a common origin, we could never be certain of their futures. The tiniest variation in trajectory, a passing dust grain, a brief outgassing event, a gravitational nudge from a distant moon, can change everything. And so, the swarm teaches us humility. It reminds us that the universe is not a machine, wound up and ticking, but a living system of change, a place where drift is inevitable. Where relationships between objects are fragile, beautiful and temporary. The moon, for instance, is slowly drifting away from Earth. Neptune's resonance keeps Pluto from ever colliding with it, and thousands of asteroids trace paths between Mars and Jupiter that are stable, for now, but not forever. Stability is relative. It is not eternal. We see this even in our simulations. Astronomers model orbits over thousands, millions, even billions of years, using supercomputers to trace how small changes ripple outward. Sometimes, a system that appears orderly for eons can suddenly destabilize. One fragment nudges another. A chain reaction begins, and what was once a cluster becomes a cloud. Could that be what we're seeing with 3i Atlas? Could we be catching a swarm in the middle of such a transition? Perhaps it was once more tightly grouped, but has since begun to unravel. Or perhaps it is entering a region of the solar system where gravitational gradients will begin to pull it apart. Even our own planets exert tidal forces. As 3i Atlas moves inward, closer to the Sun, it may begin to feel these more strongly. Some fragments might fall behind, others might be flung ahead, some might even collide, quietly, leaving behind finer dust. This dust, too, will follow its own path. Some of it might spiral toward the Sun, some might be pushed outward by solar radiation, some might linger, creating faint streaks that, if Earth passes through them, could spark meteor showers no one would know to expect. We might, years from now, see such a shower, a brief scattering of light across the night sky, and somewhere, someone might connect it back to this moment, to this fragment, to this swarm, or not. It might go unnoticed, but either way, the path continues. That is the lesson of chaotic dynamics, that the future is shaped, but not fixed. That drift is the rule, not the exception. That nothing remains exactly where it is. Not stars, not fragments, not even us. As the earth turns slowly beneath you, and you feel the hush of the night deepen, remember that we too are in motion. Our orbit shifts, our axis wobbles, our very place in the galaxy slowly changes year by year, unnoticed by the senses, and yet we are still here, still watching, still tracing the gentle paths of interstellar visitors, still measuring the fragments of swarms that pass through for only a moment, then drift outward again, scatterings written in the language of chaos. Let's now float gently into one of the oldest questions in all of astronomy, and perhaps one of the most tender. Could life, in any form, ever be carried by these travellers? The possibility stirs something deep. We see a faint object like 3i Atlas enter our solar system from the dark between stars, and we cannot help but wonder, what else rides along? Not life as we know it, not plants or animals, not bacteria in the usual sense, but the raw materials, the scaffolds, the templates, the gentle chemical hints that, under the right conditions, could someday awaken. In the earliest days of Earth, before oceans and oxygen, before cells or replication, the planet was bombarded by fragments, asteroids, comets, dust from far beyond. And within those fragments were organic molecules, simple but structured. We know this because we've found them still today, locked inside ancient meteorites that have landed here. Molecules like amino acids, glycine, alanine, valine, essential to life, but formed far away from anything alive. And so the idea grew that the seeds of biology may drift through space unbound to any planet, that some of these seeds may fall occasionally upon just the right world, at just the right time, a world with warmth, with water, with patience. This idea is called panspermia. Literally, seeds everywhere. There are many forms of it. Some suggest life itself could survive space. A spore, frozen and shielded, carried within a rock for thousands of years, protected from radiation, revived by warmth. Others propose a softer version, that life's ingredients, not life itself, are what travels. Amino acids, sugars, chains of carbon, structures that, once stirred by sunlight and minerals and time, might find their way into something more. 3i, Atlas, and its possible swarm, remind us that such journeys are not only possible, they are happening, constantly. Every object that drifts in from interstellar space is a time capsule. It carries within it the chemistry of its origin system, the temperature and pressure of the dust cloud where it formed, the radiation fields it passed through, the collisions it survived, and if fragments trail behind it, small, cool, protected, they might be even better vessels for delicate molecules. Dust and ice, preserved in vacuum for millions of years, never heated, never cracked by planetary flybys. These are ideal conditions for preservation, not for growth perhaps, but for carriage, and that alone is remarkable. Imagine molecules forming around a distant star drifting outward as part of a swarm, then passing through our solar system unnoticed. They might fall into our upper atmosphere, land in an ocean, settle into soil, and we'd never know. We'd assume they were ours, part of Earth. But they would not be. They would be older. We've found such hints already. In the Murchison meteorite, which fell in Australia in 1969, scientists discovered over 70 amino acids, many not found on Earth. They also found nucleobases, the same molecular letters used in DNA and RNA. These compounds were clearly not the product of earthly life. They were born in space, carried in stone, delivered by chance, and that was a single meteorite. Now imagine a swarm like that of 3i Atlas. Not a single rock, but a trail of them. Fragments moving together, drifting across light years, some perhaps no larger than grains of sand. Each one a chance. We don't know if these fragments have entered Earth's atmosphere before. We don't know if any will in the future, but we do know they exist, and that changes everything. Because now panspermia is not just a theory, it becomes a mechanism, a process, a gentle rain of complexity from the stars, Of course, there are limits. The interstellar medium is harsh, radiation is constant, shocks and collisions are common, and space is slow. Even at tens of kilometers per second, a journey between stars takes millions of years. Can any chemistry survive that long? Can any chain of carbon endure? Perhaps not, but perhaps some can, especially if shielded inside, buried deep in a rock, frozen into an icy matrix, protected by layers of dust. Space is cold, but it is also calm. Once adrift, a fragment may pass centuries without incident, and if it remains intact, who knows? Even if the swarm holds nothing biologically relevant, its presence is still a gesture. A reminder that systems do not end at their edges, that stars share more than light. They share material, fragments, dust, stories, and that those stories may land softly somewhere, someday, in a quiet ocean on a quiet planet, ready to be stirred into something more. This idea does not conflict with Earth's origin of life, it simply broadens it. Life may have begun here, or it may have been assisted, triggered, amplified by an object that once drifted through the stars like 3 Atlas drifts now. We may never know, but to even ask is to connect ourselves to something older, to feel the drift of time more deeply, to see Earth not as isolated but as part of a network, a quiet, drifting family of possibility. Perhaps life is rare, or perhaps it's inevitable, a natural consequence of time and chemistry, repeating wherever conditions allow. If so, then every swarm is a thread in that fabric, every fragment a seed or a reflection of one, and each passing object becomes more than a rock. It becomes a messenger, not sent, but carried, not urgent, but patient. Tonight as you rest, imagine a fragment of 3 Atlas tumbling slowly in the dark. No lights, no signals, just quiet motion. Inside it, molecules curl into stable shapes, not alive, but not inert. They wait, and perhaps, somewhere, someday, they will fall again. Let's turn now to silence. Not the absence of sound, but the profound, enveloping quiet that stretches across the universe. The kind of silence that listens, waits, and does not answer. Because in the midst of all this motion, fragments drifting, stars forming, swarms passing through, there is also the persistent hope that someone might be speaking, and so we listen. From vast radio arrays nestled in mountain basins to delicate receivers pointed skyward from desert valleys, humanity has been listening for decades, ears turned to the sky, hoping to hear something more than static. This practice, called Radio SETI, the search for extraterrestrial intelligence, has become a quiet heartbeat in astronomy. Not a rush, not a race, just a steady, patient act of attention. But what do we hear? Mostly we hear nothing. Or more precisely, we hear noise, galactic background radiation, bursts from pulsars, whispers of quasars, the sun's own radio emissions, Earth's own interference, but no beacons, no deliberate signals, no clear voices rising above the hum, and yet we continue. Because silence is not the same as absence. It may mean no one is speaking, or it may mean we don't yet understand the language, or that we're not listening in the right way, or at the right time, or with the right instruments. Into this silence, interstellar objects like 3 Atlas enter quietly. They do not signal, they do not pulse, they do not alter our receivers, but they pass through that silence, briefly crossing the space between stars, the same space we listen into. And for some, this raises the question, what if? What if such objects were carriers, not of life or of organics, but of signals? What if they were not only natural fragments, but part of something more deliberate? Oumuamua stirred these questions in 2017. Its strange, elongated shape, its non-gravitational acceleration, its silence. Some wondered if it might be an artifact, an ancient dormant probe, a relic. Most scientists rejected that idea. Its motion could be explained by natural processes. Its silence was, perhaps, expected. But the question lingered. And now, as 3 Atlas passes through with possible fragments trailing behind it, the same whispers rise again, not as conclusions, but as thought experiments. What if a civilization wanted to explore the galaxy not with ships, but with debris? What if it seeded the stars with slow, silent messengers, objects that appear natural, but carry within them structures or signals waiting to be found? The idea is speculative, but it reflects something real. The boundary between natural and artificial is often one of interpretation. A signal, for instance, might appear random until decoded. A shape might seem geological until examined in detail. A pattern might emerge only after long, careful attention. And so, in addition to listening passively, some researchers have begun turning their attention toward interstellar objects, not to hear them, but to ask, do they spin in predictable ways? Do their surfaces reflect light oddly? Do they follow purely gravitational trajectories? So far, the answer to all these questions for 3 Atlas is nothing unusual. It spins, it reflects, it moves. But still, we watch. And that watching, that listening, is its own kind of dialogue. Instruments like the Allen Telescope Array in California, or Breakthrough Listen's monitoring projects at Green Bank and Parks, sometimes target known interstellar visitors, just in case. They sweep radio frequencies, searching for narrowband transmissions or regular pulses. They analyse for modulations that might hint at information, not just noise. Nothing has been heard. But the act itself matters, because it reminds us that for all our technology we remain small, observers, listeners, quiet guests in a vast cathedral, straining to hear footsteps on distant floors. Even silence, when heard long enough, takes on shape. We notice patterns in its texture. We begin to model what signals should look like. We design better filters, wider arrays, instruments that can detect not just radio waves, but laser pulses, or gravity waves, or neutrino flashes. Perhaps one day, a swarm will pass through that isn't silent, or perhaps silence is the message, a kind of galactic hush, not born of loneliness, but of age. Perhaps civilizations do not broadcast, perhaps they drift like fragments, leaving behind only quiet traces. In this way, 3 Atlas becomes not just a traveller, but a symbol, a reminder that stars share more than heat and light, they share space, and that into that space all things pass, including us. Because we too are sending signals, radar, television, transmissions, probes. Even Voyager, now drifting beyond the heliopause, carries a message, etched into gold, silent but eternal. A greeting in case anyone ever finds it. Perhaps that's all any swarm really is, a message, not written, not encoded, but carried in composition, in motion, in silence. And perhaps, just perhaps, there is someone out there listening to us, not with radios, not with telescopes, but with quiet patience, as we do now. Listening not for words, but for patterns, for flickers, for change. And perhaps in that distant sky, our own fragments are drifting toward them now, not to speak, but simply to arrive. Tonight, as you close your eyes and the night deepens, imagine yourself not just as a listener, but as part of the message. Imagine Earth itself as a fragment, one among many, moving slowly through the galaxy, silent, small, and filled with meaning. And out there, in the dark, others drift past us. Some leave trails, some leave silence, some, like 3 Atlas, leave questions. And in the end, perhaps questions are the most beautiful sound of all. Now we drift to the edge, not the edge of the solar system or even the galaxy, but the conceptual edge, the boundary of what can be known. the place where observation gives way to horizon, and beyond which even light cannot return. In physics, this is called an event horizon. Most often it's associated with black holes, a surface beyond which no signal can escape. But in cosmology, the idea applies more broadly. There is a cosmic event horizon too, a limit to how far we can ever see, and beyond which even the fastest traveller, moving at the speed of light, could never reach us. It's not a wall, it's a boundary in time. Because the universe is expanding, and not just expanding but accelerating. Galaxies are rushing away from one another, not because of their own motion, but because the very fabric of space is stretching. This means that some regions far enough away are already receding faster than light can travel. Not because they're breaking a speed limit, but because space itself is growing between us and them. And so, there are galaxies we will never see, not because they're hidden, but because their light will never reach us. They have already slipped beyond our horizon. Now imagine a fragment like 3i Atlas, not drifting between planets, but between stars, between galaxies. Imagine swarms of fragments scattered in the early days of the universe, moving outward with their host systems, some ejected by collisions, some flung out by tidal interactions, some simply born at the edge of light. Over billions of years, some of these fragments may have crossed the cosmic event horizon, gone not just beyond visibility, but beyond possibility. There is no telescope that will ever catch their motion, no probe that will ever reach their path. They are lost, not in space, but in time. And yet, here we are, catching one fragment that hasn't drifted beyond. One fragment, 3RC Atlas, that still crosses through our light, still dances on our side of the horizon. That, in itself, is extraordinary. Because the older the universe grows, the fewer such objects we may see. In the future, as expansion continues, more stars will slip away. More swarms will be lost to the dark. Our observable sky will shrink, not in size but in meaning. Already the cosmic microwave background, the oldest light we can detect, sets a limit to what we can know about the beginning. And already some of the earliest galaxies are near the edge of detectability. Their light, stretched by expansion, arrives to us as a whisper in infrared. We build ever more sensitive instruments to catch these faint signals, but no matter how strong our tools, the horizon is fixed by physics, and it leads to a gentle realization that what we see now, what we can ever see, is a vanishing slice of a much larger whole. And so, every visitor matters, every crossing is precious, not because it tells us everything, but because it tells us something. It gives us a data point, a moment, a reminder that the universe is older, wider, and deeper than our vision allows, and it reminds us that motion continues even in silence. Even a small fragment like 3i Atlas drifting through our system for a few months or years carries within it the echoes of a time before us. It began its journey before Earth had life, before the sun had planets, before light from distant galaxies even had a chance to stretch into microwave. Its path, curved now slightly by the sun, is still on its way outward, and someday it will cross our own horizon. Just as it came from somewhere beyond the known, it will continue to somewhere beyond the knowable. We will not see where it ends, but we do not need to, because in this moment, right now, we are part of its path, and that's enough. This applies to more than just interstellar visitors. It applies to our own planet, our own species. We too are within a universe whose boundaries are shifting. We too live within a shrinking observational horizon. And yet we build stories. We look outward. We wonder. Even as galaxies fade from view. Even as the sky grows quieter. Some scientists believe that far in the future, civilizations may look at the sky and see only darkness. No other galaxies, no cosmic background radiation, no clues to the Big Bang. Just stars in their own system and nothing else. And they will wonder, was there ever more? We are fortunate to live in this brief window, a moment when the sky is still filled with motion, still open, still rich with echoes. And so, when we see something like Three-Eye Atlas, when we detect a fragment from the far dark moving in our midst, we are not just observing an object, we are watching the universe speak softly across its vanishing edge. As you drift into rest, imagine this horizon, not as a limit, but as a canvas, a boundary of imagination, a line that marks the outer edge of light, beyond which stories continue, even if we cannot hear them. And just inside that line, for now, we watch a tiny fragment pass. Now let us return to where we began, not to Three-Eye Atlas itself, but to the quiet idea that something is following it, a swarm perhaps, a gentle drift of fragments, or maybe just shadows, aligned by chance. We may never know for sure, but even if those companions are illusory, the journey we've taken through this thought has been real. We've watched as a faint object from another star system entered our sky, moving on a hyperbolic arc, not orbiting, not staying, just passing through, briefly visible, briefly known, and we've imagined what might follow behind it, companions from the same birth, debris from a disruption. A quiet trail left behind by some long ago scattering. This possibility of a swarm trailing through space opens doors far wider than the telescope's view. It invites us to think in timescales longer than civilization, to trace origins beyond our sun, to imagine processes not confined to a single solar system, but echoing between stars. We don't yet know if the fragments trailing Three-Eye Atlas are real. They're faint, fleeting, maybe statistical noise, maybe nothing. But we know that swarms exist. We've seen them in the Trojan clouds of Jupiter, in the dusty tails of comets, in meteor showers that sweep across our skies each year. Born of ancient trails, and we know that other stars likely form swarms of their own, that planetary systems eject material, that disruptions happen, that gravity nudges and dust drifts and fragments sail away from home, never to return. So when we look at Three-Eye Atlas and imagine it not as a lone traveller but as part of something larger, we are connecting it to this broader truth. The galaxy is full of quiet, moving structures, faint groupings, soft echoes. Even if we don't see them yet, they are likely there, and the idea that some of them pass through our sky, unnoticed, year after year, that's not just humbling, it's beautiful. Because it means that we are not isolated, that Earth is not a sealed vessel, that the sun is not a fortress. It means that we live in a space that is open, permeable, in conversation, not with words, but with motion. Visitors come and go, and perhaps we too are sending our own. Fragments of the early solar system flung outward by Jupiter or Neptune may now be drifting between the stars. Tiny pebbles, dust grains, ice balls, each one carrying within it a trace of our origin. They will never return, but that's not a loss, it's an exchange. And perhaps this is what Three-Eye Atlas represents most clearly, not an anomaly, but a moment of recognition, a nod between systems, a passing gesture in the long story of cosmic drift. We're often told to look for large events, supernova, planetary alignments, missions to Mars, but there is quiet power in the small, in a single rock arriving silently, in the whisper of light off its surface, in the idea that what follows behind it may never be seen, but still exists. This is the rhythm of the universe, not urgency, not spectacle, but slow unfolding, motion without destination, structure without permanence. Even now, Three-Eye Atlas continues outward. Its path, slightly bent by the sun, carries it beyond Mars, beyond the asteroids, eventually beyond Neptune, and its companions, if they are there, will follow, or perhaps they've already passed, or linger behind. The swarm, like so much in space, is not a defined shape. It is a suggestion, a soft cloud of possibility. Some fragments may re-enter the interstellar dark. Others may drift closer to planets, warmed briefly by sunlight, then fade again. Most will never be seen, but they remain. Tonight, as you breathe softly and feel the hush settle around you, imagine the solar system not as a fixed structure, but as a stage, a place where objects come and go, each carrying with them the fingerprints of a different story. Some are born here, some visit, some return, and some, like 3i Atlas and its silent trail, pass through once and leave behind only a question. And sometimes a question is enough. A reason to look again, to wonder again, to remember how much is moving, even when all seems still. Now let us settle completely. We've wandered far tonight, beyond the planets, beyond the sun, into the dark where fragments drift like ancient thoughts, unmoored from any world. We've followed a faint visitor, 3 Atlas, as it crossed through our system, trailed perhaps by a quiet swarm of companions. We've imagined its birth near a distant star, its long passage through the galaxy, its brief appearance in our sky, and we've wondered what it carries: dust, chemistry, silence, a story not told but travelled. We've listened for its signal, we've asked what it remembers, we've watched its path curve gently under gravity's invisible hand. And now we let go, let the images soften, the cold fragments trailing in the dark, the silent dust drifting between planets, the wide, quiet sky, stretching from here to horizons we can't yet reach. Feel the slowness of that motion, the patience, the age. Let it ease your thoughts. Slow your breath. Feel how small we are, not in a way that dims us, but in a way that connects us. We are part of this cosmos, part of the drift, part of the silence. Somewhere a fragment continues outward. Somewhere another just begins its long fall inward. And here we are, in between, watching, wondering, resting. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. Until next time, from this small corner beneath the velvet skies, thank you for wandering with us. Sleep well. Sweet dreams.